All right, welcome back to another lecture. We're going to talk about the binomial distribution here. This is section 2.5. And this kind of represents a shift in perspective a little bit. So far in chapter 2, we've been talking about sort of the basic notion of probability. And what we're going to do starting now in 2.5 is we're going to talk about specific kinds of probabilities that are very, very common. And the first one that we'll touch on is the binomial distribution. Make sure that you have your notes ready to go, and let's dive in. So I want to lead with a little example here that we can kind of use to build off of based on our knowledge of general probability that we've already been covering, right? So it says, suppose we draw 3 cards from a standard 52 card deck with replacement. So we're going to put the cards back into the deck before each new draw. And then it says, and we count the number of times we draw a diamond. What is the probability that out of our 3 cards, we get 2 diamonds? Now, the answer here is not 2/3, right? So I think it's kind of a common thing to want to jump to that because you see a 2 and you see a 3 and you think, oh, it must be 2/3. But no, that's not correct. We need to think a little bit more carefully. Hopefully, having just come through section 2.4 about the multiplication rule and the addition rule, you have a little bit more sophisticated understanding of this, right? So we need to think a little bit more carefully. Every time we draw a card, the probability of drawing a diamond is going to be 13 out of 52 because there are 13 cards in the deck and 13 diamonds in the deck and 52 cards in total, right? Well, 13 out of 52 it reduces to 1/4, or in other words, that's 0.25, 25%, right? 25% of the cards in the deck are diamonds. So we might think that the probability of drawing 2 diamonds would be the probability of drawing a diamond and then drawing another diamond. And since we're replacing the cards back in the deck, we can think of those as independent events. And so it would just be 0.25 times 0.25. But this is also incorrect. It's closer than 2/3, but it's still not quite there, right? It would be the correct answer if we only drew 2 cards, but we want the probability of drawing 2 diamonds if we draw 3 cards. So we actually have to think about, well, wait a second, how many ways could this occur, right? There are multiple ways that we could obtain 2 diamonds in 3 draws. One way would be to draw a diamond and then draw another diamond and then draw something that's not a diamond, which I'm just labeling as a fail, right? So diamond and fail. Another way that this could happen is we draw a diamond on our first draw, but then we fail on our second draw. And then on our third draw, we draw another diamond. Okay, and then there's one more way that we could get 2 diamonds in 3 draws, and it would be if we fail first and then get 2 diamonds in a row. Diamond. Okay, so these are all the ways that that we could get 2 diamonds in 3 draws. So actually, the probability of drawing 2 diamonds in 3 draws is going to be this, right? It's going to be the probability of diamond and fail, or diamond and fail and diamond, or fail and diamond and diamond. And once again, one of the things that you just finished learning about in section 2.4 is that all of those and probabilities turn into multiplications, and all of those ors turn into additions. So this is how that statement translates into mathematics. Now, we've already talked about the fact that the probability of drawing a diamond is going to be 0.25, right? 25% each time. So this is going to be 0.25 times 0.25. Probability of failure, right? The probability that we don't draw a diamond, well, if 25% of the cards in the deck are diamonds, then that means 75% of them are not, right? So this would be times 0.75. Okay, now that's just that first group. This is the probability of diamond and fail. But then we also could have, okay, probability of diamond times probability of fail times probability of diamond. Okay, so that's another way that it could happen. And then finally, there's one more way that this could happen, is that we could fail first and then get 2 diamonds in a row. Now, one thing that you'll notice if you're looking at these numbers is that actually this is just 3 copies of the same thing, because multiplication is commutative. In other words, we can do multiplication in any order we like. So 0.25 times 0.25 times 0.75 is actually exactly the same thing as 0.25 times 0.75 times 0.25. You'll get the same answer no matter what order you do those multiplications in. So these are just 3 copies of the same thing. So I'm going to write this a little bit differently for reasons that will become clear later, but I'm just going to say, well, this is just 3 copies of 0.25 times 0.25 times 0.75. Okay. And in fact, I'm going to take it one step further before we type our answer into Desmos, right? But we could think of 0.25 times 0.25 as 0.25 squared. And once again, hopefully it'll become clear a little bit later why I'm writing it this way. Similarly, I'm going to write 0.75 as 0.75 to the first power. Okay? So again, I know it's maybe a little bit strange to write the answer that way, but it'll become clear in a second why I'm doing that. So let's just head over to Desmos and type that into our calculator real quick. So we're going to have 3 times 0.25 squared times 0.75. Okay, so that's about 0.1406-ish. Okay. These types of probabilities are very common. So we give them a special kind of name that we call these the binomial distribution. This is an example of a binomial distribution problem. Okay, so let's define the binomial distribution a little bit more rigorously. Okay, an experiment is a binomial experiment if it satisfies the following 4 conditions here, right? Number 1, the experiment has to be performed a fixed number of times. We call each repetition a trial. Number 2, the trials have to be independent. In other words, the outcome of one trial should not be allowed to affect the outcome of another trial, right? If it does, then the experiment is not binomial. Okay. Number 3, for each trial, there have to be 2 mutually exclusive outcomes, success or failure. And we saw that in the previous example, right? You either drew a diamond or you didn't, right? So we had diamond was success and anything else was failure, right? So, and then number 4, the probability of success has to be the same for each trial of the experiment. And again, that was true of the previous example. We had a 25% chance of drawing a diamond each time. So if those 4 criteria are met, then we have a binomial experiment on our hands. Now, if we count up the number of successes, x, in n trials of a binomial experiment, then we get what's called a binomial random variable. We'll discuss random variables in more detail in section 2.7. But for now, just know that if you're counting up the number of successes, x, in n repetitions of a binomial experiment, then you get a binomial random variable. A binomial distribution describes the possible values of a binomial random variable together with their corresponding probabilities. Now, I wouldn't get my I wouldn't be too concerned about keeping all of that terminology straight. I'm just trying to describe what binomial means, right? What it means for something to be binomial. Whether you call it a binomial experiment or a binomial distribution or a binomial random variable is really not going to bother me, okay? Technically, there are like slight differences in what those things mean, but like in an introductory class, it's fine to get those things mixed up. The important thing, though, is that you understand what we mean when we say binomial. Okay, so for example, recording the number of heads in 3 coin tosses is a binomial experiment, right? You have a fixed number of trials, 3. Okay, the trials are independent. Every time you flip the coin, the probability of tossing heads is the same. Okay, for each trial, there are 2 mutually exclusive outcomes, right? Heads or tails. Okay, and if we're counting heads, then we would consider heads success and tails failure. And then the probability of success is the same for each trial. So that's a binomial experiment. On the other hand, recording people's favorite dog breed is not a binomial experiment. Okay, you don't have success and failure. Now, you could have success and failure if instead of recording their favorite dog breed, you just counted up the number of people who said poodle or something, right? Because then you would have success. Success would be, you ask somebody, what's your favorite dog breed? Success would be if they said poodle, and failure would be if they said any other breed, right? So if you were counting up the number of people who said poodle, that would be binomial. But if you're just counting, or if you're just recording the people's favorite dog breed, then that's not a binomial experiment. You don't have 2 mutually exclusive outcomes. Now, if you do have a binomial experiment, then here's some notation that we'll use to describe that binomial experiment. A lowercase p is always going to represent the probability of success for each trial, and a lowercase q is always going to represent the probability of failure in each trial. A lot of times students will be confused. It's like for some reason they can remember what P represents, but they can't remember what Q represents. So do your best, do what you need to understand that Q is the probability of failure. By the complement rule, Q is 1 minus P. Every time, right? Every single time. This is how we're going to calculate what Q is. It's 1 minus P. Little n is going to represent the number of trials. That's really not anything new because you can think of it as your sample size. Okay, so little n has always represented a sample size, and here we're just going to think of it as the number of trials. A capital X is going to represent the number of successes in those n trials, and then P of X, capital P of X, is going to represent the probability that capital X equals lowercase x. In other words, it's going to be the probability of obtaining exactly lowercase x successes among the n trials. If all of that feels confusing to you, don't worry. Take a deep breath. It's going to be fine. We'll do some examples, and you'll see that this is actually very, very straightforward. In the example that we considered on page 1, actually we've already kind of gone through this, right? But in the example we considered on page 1, yeah, we had a binomial experiment for sure. Let's just look at a couple more examples, right? So example 1 here says, determine whether the following are binomial experiments. For those that are, identify what constitutes a success in the experiment, the number of trials n, the probability of success p, probability of failure q, and the possible values of the random variable. So part A says, a player rolls a pair of fair dice 10 times and the number of 7s is recorded. Okay. So the first question we need to answer is this a binomial experiment? And to answer that question, we could go through this list of criteria that a binomial experiment has to meet, right? So number 1, the experiment has to be performed a fixed number of times. Yes, that criterion is met because I think we said that we were going to roll the dice 10 times, right? So yes, right, we have a fixed number of trials. The trials are independent. Yeah, every time you roll the dice, the probability is the same. The probability of rolling a 7 is the same. Okay, number 3, there are 2 mutually exclusive outcomes. Again, yes, either you roll a 7 or you don't, right? So we have success, which is rolling a 7, or failure, which is rolling everything else. And then the probability of rolling a 7, the probability of success is going to be the same for each trial. So I would say, yes, this is binomial. Since it's binomial, we need to identify what constitutes a success, the number of trials, and so forth, right? So success in this case is rolling a 7. Okay, the number of trials, we said n equals 10. The probability of success P, well, this is actually a probability that we've looked at before. But remember that when you roll a pair of dice, there are 36 possible outcomes. And 6 of those outcomes sum up to be 7, right? Like you can roll a 1 and a 6, a 2 and a 5, a 3 and a 4, a 4 and a 3, a 5 and a 2, or a 6 and a 1. So there are 6 ways to roll a 7. So probability of success is 6 out of 36, which reduces to 1/6. Probability of failure is going to be 1 minus the probability of success. Well, if the probability of success is 1 out of 6, then the probability of failure should be 5 out of 6, right? And then finally, we're supposed to write down the possible values of the random variable x. Well, the smallest that x could be would be 0, right? It's not very likely that you're never going to roll a 7, but it is possible, right? It could be the case that you get 0 7s, right? So x could be 0, or x could be 1. It's possible that you could roll a 7 exactly once out of your 10 rolls, or it could be that you get a 7 twice or 3 times, right? Or it could be the case, and this is also very unlikely to occur, but it could be the case that you roll a 7 every single time you roll the dice, right? So x could be 10. But x can't be 11, okay? Because you're only going to roll the dice 10 times. So it's not possible to roll a 7 11 times when you're only rolling the dice 10 times, right? So x could be any whole number between 0 and 10. Okay, so that's it for part A. Let's look at part B. It says 3 cards are drawn from a deck without replacement, and the number of aces is recorded. The first question is this a binomial experiment? And the answer is no, not in this case, right? Because we're drawing the cards without replacement. And so the probability that you draw an ace on your second draw is going to be different from the probability of drawing an ace on your first draw, because you were not replacing that ace back into the deck, right? The probability of drawing an ace on the first draw is 4 out of 52. 4 aces in the deck, 52 cards in the deck, right? The probability of drawing an ace on the second draw, if we don't replace that first ace, is going to be 3 out of 51. So no, the probability of success is not the same for each trial, and therefore this is not binomial. Okay, part C. A fair die is rolled 50 times, and the number that is rolled, 1, 2, 3, 4, 5, or 6, is recorded. Well, once again, this is not a binomial experiment. In this case, it's not because the probability of success isn't the same. It's because there is no success that's been defined, right? You're not recording the number of times that a particular outcome occurred, so we're not counting up a success. We're just recording the number that was rolled. Okay, there are not 2 mutually exclusive outcomes, there are 6 mutually exclusive outcomes. So this is not binomial. It kind of violates the whole bi part of the binomial experiment, because there are 6 outcomes, not 2. Okay, one more. And if you haven't been doing this already, go ahead and pause the video and give this one a try. But it says, in a class of 30 students, 60% are female. The instructor randomly selects one student, records the sex of the individual, asks the individual to sit back down, and randomly selects again from all 30 students. This experiment is repeated 4 times, and we record the number of females chosen. So again, go ahead and give the video a pause. See if you can decide if that's binomial. And if it is, identify all the things that we did in part A. Here's my solution. This is definitely a binomial experiment. This one is binomial. It's binomial because we have a fixed number of trials, right? We're going to repeat the experiment 4 times, okay? The probability of drawing a female is the same for each trial because we ask the individual that we choose to sit back down, and then we select again from all 30 students. And there are 2 mutually exclusive outcomes. Either you choose a female or you don't, right? So this is binomial. Success is choosing a female. Okay. Number of trials is 4. Probability of success. Well, success is choosing a female, and we were told that 60% of the students in the class are female, so the probability of success is 60%. Which means the probability of failure is 40%, right? If 60% of the students in the class are female, then 40% are not. Okay? And then finally, the possible values of the random variable x. Well, it's not very likely, but it's possible that in our 4 choices, we never choose a female, right? It's possible we get 0 females. It's also possible we get 1 female or 2 or 3 or 4 females, but it's not possible for us to get 5 females because we're only choosing 4 students. Okay. One more example kind of like this. It says we determined that some of the parts in example 1 were not binomial experiments. How might we adjust each one to make it binomial? So in particular, parts B and C were not binomial. So how can we fix those? Well, in part B, let's remind ourselves what that one looked like. So part B was when we were choosing 3 cards from the deck without replacement, and the number of aces was recorded. The issue was that we were choosing the cards without replacement. So that's an easy fix. Just replace the cards back into the deck before each draw, and then boom, you've got a binomial experiment on your hands, right? So part B, replace the cards after each draw. Okay, and then in the case of part C, the issue there was that we were just recording the number on the die that got rolled. So we didn't have a success identified. So the way we would fix that is to identify a success, right? Identify some outcome as a success. And it could be any outcome that you want. For example, we could say, instead of recording the number that was rolled, we could say the number of times a 4 was rolled is recorded. Or you could say the number of times an odd number was rolled was recorded, right? Something like that. Okay. So now that we know how to identify a binomial experiment, let's talk about computing binomial probabilities, right? Going back to the example from page 1, right? Suppose we pick 3 cards from a standard deck with replacement, and X is the number of diamonds drawn. So then X would be a binomial random variable, and this would be a binomial experiment. As we discussed on page 1, although we didn't use these particular symbols, but as we discussed, the probability of getting exactly 2 diamonds, in other words, the probability X equals 2, is not the same thing as 2/3. Instead, the probability that X equals 2 was 3 times 0.25 squared times 0.75 to the first power. Let's break that down a little bit more. So recall that, actually let me erase what I just wrote there. So recall that 3 is the number of ways that we could get 2 diamonds and 1 failure, right? We listed out all of the ways that could happen on page 1. There were 3 ways that it could happen. Well, mathematically, the way that we could write that down is as 3 choose 2, okay? Because we're going to have 3 draws, and we need to choose 2 of them to be success, right? 3 choose 2. 0.25 was the probability of success, right? It was the probability of choosing a diamond. And 2 was the number of diamonds that we wanted to select. And then finally, 0.75 was the probability of drawing a card that was not a diamond, and 1 was the number of non-diamonds that we wanted to select, right? So here's another example. Okay, suppose that X is the number of times we flip heads in 20 flips of a coin. If we want the probability that X equals 7, in other words, if we want to find the probability that in 20 flips we get exactly 7 heads, then here's what we need to know. First of all, we need to know the number of ways to get 7 heads in 20 flips, and that's going to be 20 choose 7. Okay, 20 flips, we need to choose 7 of them to be heads. Okay. The other thing we would need to know is the probability of success. Well, every time we flip a coin, there's a 50% chance that it's going to come up heads. So the probability of success is 0.5. And we want 7 successes. Okay. We also need to know the probability of failure. Well, if the probability of success is 50%, then that means the probability of failure is 50%, right? If we succeed half the time, then we fail the other half of the time, right? So the probability of failure is 0.5. And the number of failures is going to be 13, because remember, there are 20 flips, okay? And we want 7 successes. So if we have 7 successes out of our 20 flips, then that means we have to have 13 failures, right? 20 minus 7 is 13. Putting that all together then, the probability that X equals 7 would be 20 choose 7, right? That's the number of ways to get 7 successes out of our 20 flips, times 0.5 to the 7, okay? That's the probability of success raised to the number of successes we want, times 0.5 to the 13. That's the probability of failure raised to the number of failures that we want, okay? So that's how we would compute that probability. In general, we have the following formula. And if this is scary to you, hopefully it's a little bit less scary now that we've kind of been through the reasoning. But here's how we would do this, right? If X is a binomial random variable, then the probability of obtaining exactly lowercase x successes would be n choose x times p to the x times q to the n minus x, where n, x, p, and q are all the things that that we said that they represented back on page 2. Now, here's the thing. I don't want you actually computing these using this formula because it's tedious to do it by hand. And we have a built-in function in Desmos that I'm going to show you how to use that will compute these probabilities for us. But the reason I went through all of that logic is because I want you to understand what Desmos is doing behind the scenes, right? This is what Desmos is doing to calculate the probabilities that we're going to ask it to calculate for us. So let's learn how to use Desmos then to calculate these probabilities. What we're going to do is we're going to open up the graphing calculator in Desmos. Now, the calculator in Desmos that I've shown you in the past has been the scientific calculator, but we're going to want to open up the graphing calculator. If you're looking at these notes electronically, then you could just click on this link and it'll take you directly to that calculator. But I'll just show you how you can get there just from your internet browser. It's not difficult, right? So here I have the scientific calculator pulled up, but if I want the graphing calculator, all I have to do is go to www.desmos.com. Desmos.com. And then you have all these options down here. You can open up the scientific calculator. That'll open up this thing. But we want to open up the graphing calculator, right? That's this one right here. Okay, so this is what the graphing calculator looks like. This is what we're going to use to calculate binomial probabilities and other probability distributions as well. Okay, we're going to type in binomial dist into the Desmos calculator, and then once we do that, we'll be able to enter the number of trials n and the probability of success p, and then we can start to calculate some probabilities. Okay, to do so we have to click on cumulative probability, and then choose the type of probability that we want to compute. So I'll take you through all this here in a second. It'll be easier to do this if we look at some examples. So number 3 says, we toss a fair coin 20 times, find the probability of obtaining exactly 7 heads. Well, this is what we were just looking at on the previous page, right? It was 20 choose 7 times 0.5 to the 7 times 0.5 to the 13th. But we're just going to use Desmos to do it. It'll be a little bit easier. Here's the work that I would like for you to show. So in Desmos, you're going to type in binomial dist. So when you're showing your work on a test or a problem set, make sure to write this out. And then we're going to input the number of trials, right, which is 20 in this case. And then the probability of success. Well, if we're flipping a fair coin, then the probability of heads is 50%. Okay. Now, the probability we're looking for is the probability of obtaining exactly 7 heads. So I also, when you're showing your work, I also want you to write out the full probability statement, right? Probability x equals 7. Or if you prefer, you could just call it P of 7, right? So you could just write it this way, P of 7. But you know, now that I say that, maybe it would be better to just write probability x equals 7, because I think that's how it's going to show up in the calculator on Desmos anyway. So let's go over to Desmos and calculate this number. So I'm going to click onto one of these rows, okay, and I'm going to start to type binomial dist. And notice that, like, as soon as I finish typing it in, if I've typed it in correctly, it'll change from italics to normal, to normal script, right? Binomial dist. Then I need to open up a set of parentheses, and it even prompts me down here that, hey, you need to put in the number of trials, and then you need to put in the probability of success, right? We said number of trials would be 20, and the probability of success would be 0.5. So it kind of starts to graph something over here. If you want to get a better picture of that graph, you can click this little magnifying glass with a plus sign in it, and that'll zoom in on the distribution itself. So these are giving the individual likelihoods, right? The individual probabilities, right? This is the probability x is 5, probability x is 6, probability x is 7. If we want to know what those numbers are, probably the best way to do it is to click on this cumulative probability. And if I want the probability that x equals 7, oh, okay, so I said something wrong a second ago, but here's how we actually do this, because none of these options give us the probability of choosing probability x equals 7. So what we actually have to do is just use this inner option, and we'll put 7 in both locations, because if x is equal to 7, then that means x has to be somewhere between 7 and 7, right? So we put 7 in both locations. Notice that on the graph, it highlights that bar, okay, which is kind of nice. And then here we have the probability. The default setting is for these probabilities to be rounded to 3 decimal places, but if you need more decimal places, all you have to do is click on the little down arrow, and then it'll give you more decimal places. So if we wanted to take this to 4 decimal places, we would call it 0.0739, okay? If we wanted 3 decimal places, well, then we could just call it 0.074. Okay, so let's write that down. So I'm going to amend what I said here a second ago. Probability x equals 7. In Desmos, we actually have to enter that as probability x is between 7 and 7. But then the answer that we came up with was approximately 0.0739. Okay, part B. We toss a biased coin that turns up heads 60% of the time. We toss the coin 20 times. Find the probability of obtaining exactly 7 heads. So this is going to go much the same way as part A. We're going to use the binomial distribution. We have 20 trials, but this time the probability of success is 60% because our coin is biased. maybe it's like weighted on one side or something. I don't know. But that's going to be the only difference, because we still want to compute the probability of obtaining exactly 7 successes. And as we saw a second ago, the way we're going to enter that into Desmos is probability 7 is less than or equal to x is less than or equal to 7. We're going to use that inner version of the calculator. Anyway, let's take a look. So we'll do the same thing. Binomial dist. 20, 0.6. So it's plotting that one in blue. So you can see that, yeah, okay, so there's some slight differences here. And we want probability x is 7. So again, I'm going to put 7 in both locations. Okay, so it's highlighting that here. Notice that the probability decreased. It's less likely in this case. That's something that's worth pausing to reflect on a little bit. But let's write down our answer. Let me try to get 4 decimal places here. So it says 0.0146. Okay, so the probability decreased. At first glance, I think that this is counterintuitive to students, because the probability of success in part A was 50%, and the probability of success in part B was 60%. So it seems like, shouldn't the probability of getting 7 heads increase? I'll let you pause the video and see if you can come up with a response to that question. Here's my answer to that. I think that, well, I don't think I know. I know that the reason that the probability decreased is because we were looking at the probability of getting heads less than half the time. Remember that we were going to flip the coin 20 times. So getting 7 heads means we're flipping the coin less than half the time. Well, if the probability of success is more than 50%, then the probability you're going to get heads less than 7 times is going to be small, or less than half time is going to be small. And the larger this probability gets, the smaller this probability is going to get, because it's going to be less and less likely that you would get fewer heads, right? Fewer than half of your flips being heads. Anyway, so that's the answer there. Let me walk you through several more examples just to show you kind of the differences between the different options that are available to you when you go to compute a binomial probability in Desmos. So number 4 here says, according to Experian Automotive, 35% of all car-owning households have a red car. If we take a random sample of 20 households, compute the probability of each of the following outcomes. Okay, part A wants us to compute the probability that exactly 5 households have a red car. Well, we'll use the binomial distribution, because either a household has a red car or it doesn't. So this is definitely a binomial dist. We have 20 households. Now the probability that any given household has a red car is 35%. So 30.35 is our probability of success. And then we want the probability that exactly 5 have a red car. And again, to do that, we're going to have to punch this in as 5 less than or equal to x less than or equal to 5. Okay, let's see what we get. I'm just going to reuse this first one. I need to change the probability to 35%. And zoom in on it again. And I want the probability x is between 5 and 5. In other words, the probability x equals 5. And it looks like that's about 0.1272. Okay, Part B asks for the probability that between 8 and 10 households have a red car. So I'll tell you what, I'm not going to keep rewriting this binomial dist thing because it's not really going to change. The only thing that does change is the probability I'm looking for. So here I'm going to look for the probability that x is between 8 and 10. So I'm going to look for the tool in the calculator that will allow me to do this. And of course, it's the same one that we've already been using, right? I'm just going to replace the 5 with an 8 and this other 5 with a 10. And then I'm good, right? 0.346, or if I want 4 decimal places, 0.3458. Again, when you're showing your work, I want to see this entire probability statement, not just your answer. And if it's like a set of problems where this thing doesn't change, then you don't need to rewrite it over and over again, but I would like for you to write it down the first time that you go to use it, right? And of course, if things are changing around, like if you're changing the probability of success or something, then I do want you to rewrite the whole thing over again. Anyway. Okay, so that's A and B. Let's look at part C. Part C says, what's the probability that at least 2 of the households have a red car? So we want the probability of at least 2. Well, if x is at least 2, then that means that x could be 2 or more, right? X could be 2 or 3 or 4. It just can't be 1 or 0, right? So x has to be greater than or equal to 2. Right? That's what at least 2 means. Well, let's see how we would get that done in the binomial calculator here. Obviously not if I'm using the inner region. If I use the outer region, that doesn't really look like it either because I don't need these 2 different slots. If I do left, well, I'm getting closer, but this is going the wrong way. So it should be right. Okay, now I've got the right inequality pointing towards the right. I want the probability x is greater than or equal to 2. So I'm going to change the 8 to a 2. And there we go, 0.9979. Okay. Part D asks for the probability that more than 2 households have a red car. So this time we're not looking for the probability that at least 2 of them have a red car. We want the probability that more than 2 of them have a red car. In other words, we need x to be strictly greater than 2, right? Not greater than or equal to 2, but just strictly more than 2. Now, as we were just looking through the options that we have in the binomial distribution over here, you may have noticed that we don't have any strictly greater than options available to us. But what we can say is this: if x has to be strictly more than 2, then that means at the minimum x would have to be 3. Okay? So if x is strictly greater than 2, then that means x could be 3 or 4 or 5, but it can't be 2 or 1 or 0, right? So the probability that x is greater than 2 is actually the same thing as the probability that x is greater than or equal to 3. And that's how we deal with those scenarios. So this would be 0.9879 approximately. And here's how we had to enter that into Desmos. We said probability x is greater than 2 is equal to the probability that x is greater than or equal to 3, right? So this is what was asked for, but this is the way that we had to put it into the calculator. Again, I would like to see both. When you're showing your work, I want to see both things so that I know what your thinking and reasoning was. It's in your best interest to do that, to show your work so that I can give you partial credit in case you get the wrong answer, right? Anyway, so this comes out to about 0.9879. Okay. By the way, part D is what I had in mind when I was typing out these instructions down here, right? To get the probability that x is greater than some number, what you actually have to do in the binomial calculator is type in the probability that x is greater than or equal to one number higher than that. Okay, in a similar way, to get the probability that x is strictly less than some number, we actually have to find the probability that x is less than or equal to one number lower than the number that you want to find. So let's take a look at a couple examples to see what I mean there. Part E asks for the probability that at most 4 households have a red car. At most 4 means that 4 is the maximum, right? It could be 4, 3, 2, 1, or 0. It just can't be more than 4, right? So at most 4, it means that x would have to be less than or equal to 4. Okay. In the calculator, I think that's going to be the left, right? Because right now this is pointing to the right. We need it to point to the left so that we have a less than. And we want the probability x is less than or equal to 4. So 0.1182 approximately. Okay. And then finally, part F, we want the probability that less than 4 households have a red car. So now we're not looking for the probability that at most 4 have a red car. We just want to know the probability that strictly less than 4 of them have a red car. We want x to be strictly less than 4. Well, as we discussed a moment ago, there's not going to be a way to do this in Desmos. What we have to do is we have to say, well, if x is strictly less than 4, then that actually means that x is less than or equal to 3. Okay? So that's what we'll punch into the calculator. We want less than or equal to 3. That's going to be 0.0444 approximately. Okay, so that's how the binomial calculator works in Desmos. One last topic. So for reasons that will become clear, when we're talking about binomial distributions, we like to talk about the shape, center, and spread of those distributions. As far as the shape of a binomial distribution is concerned, it's going to be approximately bell-shaped, as long as certain conditions hold. So, for example, looking at the distribution that we have here, I would call this right skewed because we have all these values to the right. But if the probability of success gets close to 0.5, then it becomes bell-shaped, right? Or if the number of trials increases, right, then once again it becomes approximately bell-shaped. There is still a little bit of a tail, but that's going to become less of a problem the larger the larger the number of trials. Okay. Anyway, the moral of the story is that as p gets close to 0.5, or as n gets large, the distribution is going to become bell-shaped. As far as the center is concerned, we use the mean to measure the center of this distribution. And so to discuss what the mean of a binomial distribution is, I think it's helpful to remind ourselves that the mean of a distribution is an attempt to describe the average Joe. And so when we're thinking about probability distributions, it's helpful to think of the mean as the average Joe, what we would expect to encounter, right? What we would expect to happen. So we call this the expected value. Okay. So that's sort of one of the first takeaways here, is that when we're dealing with probability distributions, the mean of a distribution is the same as the expected value of the distribution. They mean exactly the same thing. So to give you an example, let's say that we flip a coin twice. If we flip a coin twice, right, there's a 50-50 chance that we get heads or tails. So the expected number of heads would be 1, right? Because we're flipping the coin twice, we expect to get heads once. So the expected value would be 1. Okay, that's my dog. Just he wants to get out, but let me finish this problem, then I'll take him out. So we would expect to get heads once. So the mean of the distribution is 1, right? So the mean is the same as the expected value, and it's just 1 in this case. When we interpret the mean as the expected value, we'll usually round to some number of decimal places that make sense, and I'll show you what I mean by that with an example below. In the case of the binomial distribution, the expected value, or in other words the mean, is just n times p. We'll talk about why in more detail in section 2.7, but for now, I think it intuitively makes sense that that's what the expected value would be. Because think about it, if you have n trials, and each trial has a probability p of ending in success, then you would expect n times p successes. For example, let's say that 15% of people own a dog, right? If you sample 300 people, you would expect 45 of them to own a dog, because 15% of 300 is 45. This is just n times p, right? So anyway, that's going to be the mean of our distribution, n times p. So that's how we measure the center of the distribution. Then the spread of the distribution is going to be the square root of n times p times q. I won't give as much detail about that here, but again, we'll discuss it in more detail in section 2.7. Here's the moral of the story. If x is a binomial random variable, then the mean of the distribution is n times p, and the standard deviation of the distribution is the square root of n times p times q. Let me just give you a couple examples of that. Okay. So number 5 here says, according to Experian Automotive, 35% of all households have a red car. So this is the same scenario as before. It says, suppose that 412 people are sampled. I have a little typo there. I'll fix it in yours, so yours won't have this typo, but suppose 412 people are sampled, and let x be the number with a red car. Part A asks us to compute mu sub x and sigma sub x. Well, mu sub x, right, the mean of the binomial random variable x, right, mu sub x, is n times p, which in this case is 412 times 0.35. Okay, 412 times 0.35. Let me type that into my calculator. So that comes out to 144.2. Okay, there's the mean of our distribution. The standard deviation of our distribution is going to be the square root of n times p times q. So that's going to be the square root of 412 times 0.35 times q. Okay, well, q, remember, q is 1 minus p. 1 minus p. So, since p is 0.35, q would be 1 minus 0.35, or in other words, 0.65. Okay, so let's write that down. Okay, and then we can type that into our calculator, right? So we'll do square root of n times p times q. So that comes out to about 9.7-ish. Okay, about 9.7. Notice how much easier it is to compute standard deviations when you're dealing with probability distributions. Okay, this is a much easier thing than back in chapter 1, right? But now we have a couple follow-up questions. Part B says, what number of households in this sample would you expect to own a red car? Well, remember that the expected value is just the same thing as the mean, right? The expected value is equal to the mean, which is 144.2. But that answer doesn't make a ton of sense. I mean, it's correct, but if you were at, like, imagine somebody asked you how many households in your sample had a red car, you would never say 144.2, right? How can 0.2 households own anything, right? It doesn't make sense. We would just round. We would just say 144, right? We would expect 144. We would expect 144 red cars, right? Or we could say 144 households to have a red car. Okay. Now part C. What if you collected 10 samples of 412 households each? Okay, how many households in total would you expect to own a red car? Well, in one of our samples, the expected value was 144.2. So in 10 of our samples, the expected value would be 10 times this number. Okay? So it would be 144.2 times 10, which is 1,442. Okay? So if we have 10 samples of 412 households each, that means we have 4,120 households. And out of those 4,120 households, we expect 1,442 of them to own a red car, right? We would expect 1,442 households to have a red car. All right. So that will do it for section 1.5. Thank you for hanging in there, and I will check in with you again in the next one.